Good morning, everyone. Thank you for joining today's webinar. So our speaker today is Dr. Haifang Wen, PE, and he's currently an associate professor and director of Washington Center for Asphalt Technology, AASHTO accredited at Department of Civil and Environmental Engineering of Washington State University, and graduate coordinator of Geotechnical and Transportation Group. He teaches and researches on infrastructure materials and design. He has published more than 70 journal papers and numerous conference papers. He has made significant contribution to the utilization of sustainable infrastructure materials for construction, based on work on NCHRP, NSF, FHWA, DOTs, local governments, and industry. His research on the recycled concrete was recognized as AASHTO high-value research projects. A few of his papers are selected as practice-ready papers, which made a contribution to current or future problems or issues for practitioners. He is serving as an editorial board member of International Journal of Geotechnical Engineering and Geological Engineering. He's also currently serving as a member of NCHRP 01-62 ASCE committee and FHWA's STIC committee. He has served on numerous TRB committees and NCHRP panels. He received Outstanding Faculty Researcher Award by the College of Engineering and Architecture of Washington State University and Outstanding Mentor Award. He is elected as a fellow of ASCE in 2021. And today his presentation will be titled Long-Term Bond Characteristics of the Interface Between Substrate and Overlays in Shotcrete Applications. Let's have Dr. Wen.
Right, thank you, Doctor. So I appreciate the opportunity to present on the shotcrete, which is a study funded by Tradula and WashDOT. So we'll talk about first of all, I'd like to acknowledge my co-presenter, Dr. Ayumi Manawadu. She is a scholarly assistant professor at Washington State University, and Dr. Pijun Qiao, who was a former professor at Washington State University. So for the shotcrete, for this topic, as many of you know, shotcrete is getting more popular for vertical and overhead applications because it's very easy to apply relative to traditional concrete, as you have seen from the picture on the right side. And the past studies has shown that shotcrete itself as a material is similar to a conventional concrete in terms of the material properties like the strength, splitting strength, and other material properties. And also, the previous studies have shown that in terms of long-term durability, such as like freeze-thaw, there was not much difference between before and after the shooting. And you have seen from the picture, this shotcrete was shot to the structure instead of a cast for conventional concrete. So there was a concern that before or after shooting, the properties of the concrete may have been changed, but based on the previous study, that we have not seen much difference. And one of the concern is that when you apply the concrete to existing structure, especially, will be the bond between the new shotcrete and the existing structure will be an issue in terms of bond. So that's the topic of today. And the studies have shown that there could be a few factors that affect the bond between the shotcrete and the substrate, whichever it is, either existing concrete or existing shotcrete. And the factors that can affect the bond between the two layers of material can be roughness, is smooth or rough, is clean, or can be there's debris, or even the Q compound. Or for the existing material underneath material is in good shape or has been deteriorated. So those all can affect the bond performance. And the other performance concern can be related to freeze-thaw, especially in the cold area. The freeze-thaw may affect the bond performance in the long term. So currently, there's a lack of the specification or guidance on the test method, and to ensure the long-term performance, specifically what test you use and what surface preparation between the before you apply the shotcrete. So the objectives of this studies, number one is to determine is there like a test method that can capture the bond performance, and number two is what kind of surface preparation we need to do for the substrate, and so we can achieve good performance. And number three is that what's the life of the bond between the shotcrete and the substrate, for example, concrete. So for this study, we have done for the materials and the test. So traditionally, for the overlay performance, is that you have the substrate, which is either concrete or existing shotcrete. That you apply the shotcrete, and then you will drill into the substrate and using epoxy to attach a steel disc, and then you pull until there's a failure. So the failure can be within the substrate and at the interface, or within the shotcrete, depending the conditions of the shotcrete, the bond, and the substrate, whichever is stronger or weaker. So it can happen in all those three scenarios. So the ASTM, the ASI has some number that typically for the pull-off test, we call this one pull-off test. Typically, the bond strength need to be 1 megapascal or 145 psi. So, and also the test method we're talking about here is typically used for the field and not that easy to do in the laboratory. So that's why we try to come up with some new test method for the laboratory. So one of the idea is to make this butterfly sample, as you have seen from here. So as you know, for concrete, pulling or tensile test is not that straightforward. There are many complications. So one way to avoid many issues, make this butterfly, and also for the fracture test, kind of like a traditional fracture mechanics model 1 or model 2 is you put a notch between at the interface, so it can do this fracture mechanics testing. So in the red here, we put some tape between the two layer materials, and there'll be a notch or crack, a simulation of crack before the test. So this based on the final element test. So, and then the design angle determined to be the 45-degree, and based on the final element results. So that's the angle you see here. That's the 45-degree angle. The advantage of using this butterfly test sample is that number one, it group better. So because you have this wedge here, so for compared to cylinder sample, so typically that's you have to anchor it. So this one you can use the friction and the support from the wedge to pull the sample, so it grips the material better. and a relatively small size. You can do it in the lab, and you can apply the load and by minimize the bending. So for tension test, and the bending is a concern. So sometimes you don't know the failure is due to the tension or due to the bending. So by doing this method, there's a potential that can be minimize the bending, and we can, because of the shape, and we can almost guarantee that the failure will be at the interface or close to the interface. So those are some advantages for using this sample design. In terms of the bound test, we have tried two types of the bound strength. One is the strength test, the other one is fracture test. For the strength test, one of them is the tensile strength. As you have seen from the slide here, you make a sample of the concrete and overlay, you pull it, and hopefully there will be a bound failure at the interface. And the other one is the shear interface. So you'll be supporting on one side, push down from the other side, and there will be possibly bound failure at the interface. And the other test will be the fracture test. That's the butterfly we're talking about. For the model one test, you'll be doing pulling and with the crack existing notch in place already. And those the one model one test. And then you have the model two, and you will be doing the shear test instead of the tension. So that's the model two fracture mechanics test. So these are the materials we used in this study. You have the existing, the cast in place concrete, and then the shotcrete mixed design. These are from the previous studies that come up with these two mixed designs. For the sample preparation, especially for the butterfly, so you will be cast the concrete in this panel for making them different samples, and for our concrete in the plywood. Then what we do the surface preparation of the concrete. You either do the chipping, sandblasting, pressure washing, or you don't do anything of the existing concrete. We call that as cast. Then what you do is you flip over, and then you place the shotcrete. So here's an example that's the concrete before application of the shotcrete. So we use the three different methods, or specifically four. One is you use the sandblasting to prepare this concrete surface, so make the little bit rough, or use the water pressure method to make the surface a little bit rougher before you apply the shotcrete, or you'll be using this chipping method, so make the surface even a little bit rougher. And then the company called Coco Construction, they helped us do this surface preparation, sandblasting, pressure washing, chipping, and then after that, they will do the clean up the surface, remove those dust, and shoot the shotcrete into the panel. So that's the preparation. And then from there, you got this butterfly sample. You can do it in the laboratory. So for this is what it looks like in the laboratory. So you do the shear test of the butterfly, or you do the tension. This is the sample of the butterfly. So you can pull the sample. So that's the mode 1 and the mode 2 sample testing. So this is a typical test result. When you break the sample, you have this peak load and then failure, right? So, and from there you can get the fraction energy of the bound. The other test is that for the strength test. For the strength test, which is different from the butterfly, test that you will be prepare these panels of concrete, still do the surface preparation using the pressure washing method, make the surface rougher, hopefully increase the bond, or the chipping method, or the sandblasting method. So all the intent were to make the surface a little bit rougher, so hopefully make the bond higher. So then after you do the surface preparation, you blow off the dust, and then you can shoot the shotcrete vertically to the panel. And then you bring back to the lab, and you use the water jet to color the sample like this way. So you can drill it using the coring method. The problem will be during the drilling, you're applying the torque, the shear, it possibly can damage the bond. Sometimes the bond can be really weak. So, and then you got this sample, you can do the tension test, like what you have seen here, just pulling the sample. So there will be possibly bond failure between the shotcrete and also the concrete substrate. Okay, so that's the one of the test method. That's the tension test method. Okay, and the other one will be the shear test, and you have seen here that you have the support on one side, and then push down from the other side. There will be a failure in the interface of the bond. So that will be the shear test. So, and then in terms of the result, let's look at it. So if you look at the blue one, that's the tensile strength. You see the C, that's a chipping method, has give you the highest tensile strength, followed by the pressure washer surface preparation, and then sandblasting and do nothing, give you the lowest. So any surface preparation would increase the bond strength. So especially for the chipping method. So the ACI has a specification. It need to be like 1 megapascal or 145 psi for the tensile strength. If you look at it here, only the chipped surface preparation and the pressure washing can give you the bond strength higher than the 145 psi. The sandblasting is a little bit lower, and the as cast, which means you don't do any surface preparation, give you the lowest bond. For the orange one, that's the shear strength. That's why you can see the chipped surface preparation gives you the highest shear bond, and interestingly, followed by sandblasting, which give you higher shear bond than the pressure washing, which is a little bit opposite compared to the tensile. Tensile for pressure washing give you higher tensile strength. So in any case, the as cast give you the lowest the strength, either tensile or shear. Okay, so exactly why for the pressure washing give you higher tensile but a lower shear compared to the sandblasting, we think for the sandblasting probably generates some dust, and the pressure washing method clean those dust and the interface, which for tension maybe is very sensitive to the cleanness of the surface. Maybe that's why tensile strength is higher when you're using the water pressure washing method. For the shear, the sandblasting give you maybe this sandblasting surface preparation will give you higher roughness compared to what pressure washing method. So that's our hypothesis. In terms of the butterfly test method, which is the fraction energy, because you do place the notch before the test, and it follows the pattern of the shear. As you see, the chipped method surface preparation give you the highest fraction energy, followed by the sandblasting, then pressure washing, and as cast. So seems the mode 2. Again, for mode 2 is also a shear test. That's makes sense. A kind of like follow the same pattern as the shear strength test. And then we wonder, like, for the interface failure, there can be two typical failure method. One is the adhesive failure, which means it's happening between the aggregate and the paste. And the second method of the failure can be cohesive, so it's happening within the paste and the interface. So we use the imaging method to look at how much the aggregate is exposed. That gives us an idea is the adhesive failure or cohesive failure. So if it's adhesive failure, which happens at the aggregate and the paste, you will see more aggregate or the rocks exposed. So based on the imaging method, you will see these two, those are the chipped method. You will see they are more aggregate exposed, and followed by the pressure washing method, and then sandblasting and edge cast. So it has least aggregate exposure. So that also explains this for the after the tensile test, why the chips method give you the highest tensile, followed by the pressure washing, sandblasting, and do nothing. So that's the adhesive failure and the cohesive failure. Then in terms of the roughness of the surface, especially the concrete, the substrate, we want to measure the texture, how rough it is. So we use this laser scanning and to scan the surface. You'll see for the chipped surface preparation, which give you the highest surface texture or roughness, and followed by the sandblasting here, and also then water pressure washing and edge cast. So that kind of like explains why for the shear, which is sensitive to the texture, the chips method and the sandblasting give you higher shear strength. So that's from the laser scanning. And we also look at the relationship between the normalized tensile and the normalized shear and normalized fracture. Normalized means relative to the edge cast surface preparation. And they will look at the relationship between those normalized bound strength and the texture depth from the laser. And in general, the trend will be if you increase the texture depth, and you'll see bound strength increase, especially for the fracture, for the shear, right? And for the tension, it's a little bit scattered, right, for the blue one. So I think for shear is more related to the texture of the surface compared to tension. So from here, we also see, if you look at the standard, we probably look at somewhere here, that's give you enough shear strength. And then we look at the long-term durability of the interface bound. Long-term durability, specifically, we look at the freeze-thaw method. So for the freeze-thaw, so it can be affecting the bond or accelerate the bond failure because the water will be freezing and pushing the material away from each other. And also that can be related to the air void in the system. So, and typically what you do is you do the freeze-thaw in the chamber, and based on the ASTM, the C666, and the cycle the temperature from a -18 to 40 degrees, and you do 8 cycles a day, and each time you're measuring the dynamic modulus, and the ASTM give you a recommendation after 300 cycles of freeze-thaw, you're supposed to return the dynamic modulus by 60% or higher right? So that's one indication. So in this case, we put the samples in the chamber, do the freeze-thaw cycles. We didn't do the dynamic modules, but instead, we do the strength test or the fracture test every 100 cycles, 0 cycle, 100, 200, and 300 cycles, as you can see here. And you increase the durability, the freeze-thaw cycles, all the strength will be decreasing. This is the tension. And also the same thing applies for the fracture energy. We only did 0 cycles and 300 cycles. You'll see there's a quite decrease of the bond strength. So the ASTM said after 300 cycles, the dynamic modules supposed to return 60% or higher, which we don't have dynamic modules. If we use the strength as an indicator and to keep the 60%, only the CHIPS method and CHIPS method can give you 60% or higher retention after 300 cycles of freeze-thaw. So, and some of the bond is really weak, especially for the edge cast. It didn't even survive sometimes the 300 cycle, just falling apart itself. So if you look at the trend here in general for any of these tensile strength, or you will see for different surface preparation that when you increase the cycle numbers, they all start decreasing to different levels. And you can try to fit the curve a little bit, using different models, polynomial or different ways, so you can do some statistical analysis. So, and what we like to know is that how soon they can survive, and the weathering for this bond. So we feed the data in this probabilistic damage model, try to quantify the relationship between the freeze-thaw cycles and the bond deterioration. So those are some of the models we used, and I'm not going to go through in detail. So basically, that what you will see here, that for again, that depends on the reliability and the damage, right? So how soon, how many cycles takes them to reach the failure, and also based on the weather condition in eastern and western Washington. So we know that eastern Washington and western Washington, they have a different climate. On the east side, there's more freeze-thaw cycles. Based on the previous study, they predict 1 year is almost 40 cycles of freeze-thaw in Pullman. And on the west side, SeaTac Airport, they only have like a couple of freeze-thaw cycles. Again, but that depends on, we study another database, they predict a little bit different number of freeze-thaw cycles for the west side and east side. So on average, we take the average, right? For the east side in Pullman, we take an average from different studies. We take like 42 cycles of freeze-thaw a year versus only like 6 or so on the west side. And you will see that this is the number of the cycles, and for the west side and the east side, and also for different probability, 50% and 90% probability. You'll see that the life of the bond for eastern Washington, using Pullman example, only can last for a few years. Then it will drop to 60% or lower, and for the 50% probability, while on the west side, it can survive a few decades, again, depending on the CHIPS method, which give you longer life of the bond, pressure washing, and sandblasting. So, and for 90% is a little bit different. So, but you can see the difference between the eastern Washington and the western Washington. that the Eastern Washington, in few years, the bound will be considered a field, and while on the west side can last a few decades. So again, Pullman is just one city for Eastern Washington, and if you go to different places, the weather may be different from Pullman. The life here will be a little bit different. Some cities are a little bit warmer than Pullman, some area in the Eastern Washington a little bit cooler, especially getting into the mountain area. But on the west side, so this is the airport area. So another consideration is that this we consider the worst case, which means whichever the surface freezes down. But we know for concrete, depend how deep, how thick the concrete, it takes time for the frost to penetrate the concrete, right? So if the concrete or shotcrete is thicker, and the number of freeze down cycles will be lower, which means the service life will be a little bit longer than what you have seen here. This is the worst case we are using as estimate. So basically, the bottom line that from this study, which we look at the shotcrete and the concrete bound, and for tensile strength, there are different scenarios. For tensile, sometimes you apply the shotcrete overhead, like a tunnel or overhead, those places, which tension is very important because the shotcrete can fall down from the substrate. So in that case, we see that the surface preparation, the chipping and the pressure washing, they can meet the standard. While the sandblasting and edge cast surface preparation did not. So those are critical for the overhead. You don't want to shotcrete or any material drops from the overhead tunnel while there's a passing vehicle, right, or pedestrian. So in terms of the shear bound, let's see if you apply this shotcrete on the slope method to stabilize the slope, for example, or the landslide, and we see the chipped method give you the highest bound, and followed by the sandblasting and pressure washing and edge cast. So apparently the surface roughness of the concrete will be critical for the shear bound. From the laser scanning method that we look at it, so we need to achieve this texture depth before you apply concrete, so you can have a good bound, especially for the shear, right? So that's the one we recommend for the construction of the shotcrete. So, and then the fracture energies from the mode 2, the butterfly, they pretty much follow the same strength as the shear bound strength. In terms of the freeze-down cycles, durability, so we saw the chipped method surface preparation give you the best durability and meet that 60% retained strength if you use the chipped method. So while the other method didn't meet that standard. So definitely we would recommend that you have to prepare the surface, right? And to a certain degree, and also depending on the location, if the region, the project location has a lot of freeze downs, like Eastern Washington, we will need to prepare the surface much better or do something else. Otherwise, it will not survive many years. While on the west side, which is a little bit warmer, has less numbers of the freeze down cycles, the chipped method and the pressure washing can give you a few decades of the bound life. And of course, there's more studies need to be done. One is look at the microstructure, look at the bound, why there's a failure, what kind of failure, it's adhesive, cohesive, all those things we need to look at more closely. And also look into other methods so we can increase the bond durability, especially in cold areas that has a lot of freeze-thaw cycles. For example, add the steel fiber in the shotcrete has been reported to increase the durability of the bond. Or before you apply the shotcrete, you can apply a layer of the cement ground, hopefully increase the bond between the shotcrete and concrete. Or you can use a physical method using the mesh, and or the anchor. So mesh can somehow support or even collect any debris from the shotcrete if it's falling apart. Or the anchor method, right? You are physically anchoring the shotcrete to the concrete or the substrate. Another concern would be, especially on the west side, and because of the seawater, which has a lot of chloride, and how would the chloride ion affect the bond durability? That'll be another concern. We recommend more studies. So with that, I would like to thank the Washington Department of Transportation for funding this study. Also, the National Center for Transportation Infrastructure Durability and Life Extension also co-found this project, and appreciate the Civil and Environment Engineering Department and the Washington State for the support of the student, and the Conco Construction Company, and which did the sample preparation and the shotcrete application for us, and many others who have helped this project. So with that, let's conclude the webinar. I'll be happy to answer any questions. Go back to you, Dr.
Sure. Thank you, Dr. Wen. It's a very great and impressive presentation. So anybody have any questions? Please feel free to ask Dr. Wen. Amir, do you have any? No? Okay.
No, thanks for your presentation. It was awesome.
Sure.
Thank you.
How about Hafiz said, Ali? Do you have any questions? No? Oh, okay. Actually, I have one. So I'm quite interested that whether the moisture content of the substrate may have any influence on the bonding strength and shear strength besides the texture of the surface.
Yes, and we look at the literature, and also the agency survey. So typically agencies would assume that if you moist the surface or bring to the saturated surface dry condition will help the bond. But from the literature, the papers we look at, there's a controversy in terms of the moisture effect on the bond. Something like, yeah, it helps, and sometimes researchers reported like actually it hurts the bond. So there was no conclusion on that side. That's why in this study we didn't include the moisture effect, and we just did it as dry, as casted. So,
okay,
good question.
I got it. So we have a question from Hafs. Thanks, Professor Haifang, for wonderful presentation. I have a question. Did you find any limitation about in-house testing method?
So I'm not sure understand it correctly, but I try give an answer that well, lab method, as always, we use the lab method to try to simulate the field conditions. We do as much as we can. Of course, there'll be some limitations. For example, the surface preparation, the concrete, how we prepare maybe a little bit different from how it's prepared in the field. So, and all those bond, tensile bond, shear bond, and also the fracture method, I think we try to make it close to the field condition, but I know it's not 100% there. So I think we did the best we can not to bend the sample when we do the tensile bond or shear bond, but there possibly, or maybe there are some kind of levels of the bending which may complicate the test results. So that's possible. So if I answer your question.
Great. So another question that I'm interested is that in practice, when people apply the shotcrete on the concrete columns or whatever structures that need to be repaired, do they spray water on it in advance, or?
Yes.
Is there any cleaning procedure for like cleaning the debris and dusts?
Well, so there's a different method. Often you have a prepared surface before you apply the shotcrete. Some agencies will ask you you blow using the air, compressed air, blow the surface to remove those dust or debris. Or you can use the water pressure method. So in this case, the Conco company who helped us do the sample, they use the compressed air to clean a little bit. But I know some agencies will require you use the water method to clean it. So yeah, that's another factor that can affect the results. But I know a lot of agencies, they want at least have some moisture on the surface before you apply the concrete, even though there is not a conclusive findings on that, the jury is still out on the moisture effect.
Okay.
Excuse me, I have a question.
Yes.
You have proposed FRC fiber reinforced concrete for increasing the bond between shotcrete layer and substrate. My question is how if our steel fibers can help to increase the bond behavior. I cannot figure out, because I think adding steel fiber in concrete will decrease the bond between FRC and another material.
Right, very good question. So that's from the literature. They found that they try different fibers in shotcrete and try to see that which one will help. They found that the steel fiber helps increase the bond, but not the plastic fiber, interestingly. So we are not quite sure, because the literature didn't explain why steel fiber works, but not the plastic fiber. So that'll be an area that will be interesting to work on to figure out, more fundamentally what's caused the difference, right? So yeah, I don't have the answer by reviewing the literature. So that'll be interesting to look into.
Thanks.
Yep.
Thank you, Dr. Wen. So if you have more questions, please feel free to contact Dr. Wen. Dr. Wen, if you don't mind, probably you can leave your email.
Yeah, so maybe I don't have the email here, so I can add at the beginning of my email. So that'll be, let me see, put it here. So my email will be, I can type here. So if anybody has a question, please feel free to email me. So.
Sure. Thank you.
Yep.
Thank you. Great. So the online video recording will be available in our YouTube channel in a couple days. So if anybody is still interested in it, or somebody just missed it, just tell them that it will be available in a few days. And again, thank you very much for your presentation, Dr. Wen. And Hope you guys all have a good day. Thank you.
Yeah, thank you, Doctor, and thank you everybody for your participation. So thank you.
Thank you. Have a good one.
Bye bye.